Okay, hello everybody, and welcome to today's event on the networking channel. Today we're going to have an exciting panel called Crafting Principled Machine Learning Architectures for Network Systems. This panel addresses an important intersection of networking and machine learning. We have two very distinguished panelists here today who are going to help us explore how machine learning and networking, these two exciting and contemporary areas, can lead to more principled and effective solutions. So we have two world's experts. We have Sanjay Rao, who is professor in the School of Electrical and Computer Engineering at Purdue University. He receives a bachelor's degree in computer science and engineering from the Indian Institute of Technology, Madras, and his PhD from the School of Computer Science, CMU. He has been a visiting researcher at Google, AT&T Research, and Princeton University. He is somebody who is very highly decorated and knows an incredible amount about this area. He's a recipient of the National Science Foundation Career Award. He's won the Symmetrics Test of Time Award and is an ACM Distinguished Member.
And
Let's see.
then, okay, and then be my pleasure to introduce Bruno. Bruno Ribeiro is associate professor of the same department at Purdue University, and a visiting associate professor at Stanford. He was there last year, and he received his PhD from UMass Amherst, and was a postdoc fellow at CMU. Bruno received the NSF Career Award in 2020 and an Amazon Research Award in 2022, and co-author of multiple Best Paper Awards. And I'd like to add that it's a pleasure for me to have Bruno. I know Bruno since he was a kid in the lab, and grew up to do the master's thesis. Was excellent and a very nice person to work, excellent person, excellent researcher, and went to UMass. So it's really a pleasure to have Bruno here with me. I'm really delighted for that. And Sanjay, please start. And we
Yes.
have exciting word now, okay? So, oh no, I sorry. Before you start, Matt wants to say a few things. I'm sorry, Matt.
Oh, no, that's great. I can just say a few quick things about the networking channel. So this is an event today. Just so you know, we have events like this every 2 weeks, and everybody's very welcome to attend all of them. We're going to have another event in 2 weeks. Please feel free to attend. Yeah, we can get started. We're planning to make this a very, kind of informal discussion. So audience, please feel free to join in. There's a Q&A feature at the bottom of your screen. The panelists would love to hear your questions and answer them. If it's helpful for you to see what's being said transcribed on your screen, there's an option for that at the bottom of your screen as well. And there's a button down there to translate our spoken words into other languages as well, if that's something you would like. So yeah, Sanjay, feel free to go ahead and proceed.
Yeah, thank you so much, Matt, and thanks, Edmundo, for the invitation. So this is work that Bruno and I have been working on along with our students and collaborators over the last few years. And as you might know, I come in from a networking background, and Bruno comes in with an ML background. And so really some of our work is at the intersection of ML and networking. So in fact, let me start with a couple of slides from a panel that I organized in SIGCOMM last year, where Bruno was one of the panelists, along with a few others like Mohammed and Keith and Benaz. And we started off by saying, look, let's look at how ML has evolved at SIGCOMM, right? So I started attending SIGCOMM around 2000, and I can practically remember no papers related to ML back then. And in the next decade, I would say it was in what was called an exploratory phase, where you might occasionally see an ML paper in topics where it seems somewhat natural, like things like packet classification, anomaly detection, diagnosis, and so on. But if we kind of look at the last 5 to 10 years, there's been the growth spurt where we're really seeing a lot of papers, but not only are we seeing a lot of them, they're getting into what we would consider some of the core networking topics like congestion control, video coding, video streaming, and traffic engineering, and so on. So really, the question is, where next? Where are we? Where do we see this going over the next decade or so, right? So I'll make some introductory remarks. Why are we excited by ML for networking? There's some very obvious things, right? So networks are working in very uncertain environments. You need to make decisions based on what you might expect the conditions to be. So things like bandwidth, loss, what the future network conditions are, and so on. You might design networks where or infrastructure where you need to know the future traffic patterns or predict them, future access patterns for things like CDN edge provisioning and so on, what the resource requirements are. So you have a variety of systems that need to make decisions under uncertainty, right? Where things like video streaming, we're trying to decide what quality to pick. Video conferencing systems, where you're trying to figure out how much redundancy to have in your error correction codes and so on. And a lot of resource allocation problems, things like traffic engineering, right, or allocating resources in shared clusters, whether it be cloud computing clusters, GPUs, and so on. So these are just at the tip of the iceberg. But what makes ML for networking challenging? So what makes it such a unique and interesting domain? I think the first aspect of it is that you might have rare events that occur probably not that rarely, right? There could be traffic surges, failures that you have not seen, very diverse failure nodes. And one of the artifacts of this is that your training data is unlikely to have covered all the scenarios that one might expect. So we have anecdotes where network operators make configuration changes. They're planning a series of executions, but in the midst of the execution, there's some failure that occurred, and somehow the combination of that leads to the network working with degraded capacity, right? So all sorts of interesting modes that have to be considered. And at the same time, dealing with rare events is quite important in this context because this is critical infrastructure. Operators care about several nines of performance. And a lot of these off-the-shelf ML approaches, and that's a term we're going to use to refer to things like standard neural networks and any of the conventional tools that you can just use off the box, are not quite positioned to deal with these types of scenarios that are not in training. The other kind of thing that we talk about are some of the data-driven decisions, right, which is the norm in networks. Unfortunately, there are a lot of pitfalls that one would have to be careful about. So, for example, let's say you're observing data from a video streaming session. You might look at the data and reach an erroneous conclusion that low video quality is associated with rebuffering. But in reality, that might be because the network bandwidth is a confounder, and sessions, and under weak poor bandwidth conditions, sessions might experience both low quality and high rebuffering, right? And what this really means is a lot of these ML tools that are available are limited to what we call observational predictions. And they're good at telling us how an existing system would perform in the future, but a lot of the tasks that we deal with in networking really talk about what would happen if I made a change, if the system picked a particular bit rate in response, or if I changed the way adaptation is done. And this requires something called causal reasoning. So what I'm going to do here is hand over to Bruno, who's going to talk a little bit about some of the challenges and some of our work, and then I'll come back and wrap up.
Thanks, Sanjay. Can you see my screen? Yeah, okay, good. Yeah, so the challenge is really that there are a lot of interesting ML questions in networking and networking questions for ML. One is, how do we do robustness to these changes, right? So if you see events that will not have, you haven't seen in training, and when you deploy, you see these events, so how would the ML method deal with those cases to generalize outside the training? And in machine learning, we call this out-of-distribution robustness. The other question is regarding trust and deployment. is the prediction I'm making on the system actionable? Meaning that if my machine learning method is only predicting the future of the system, assuming that the system is not going to be, is only predicting the future of that system without that system changing, then when I see a prediction I don't like and I intervene on the system, how would that intervention affect the future of the system, right? So the ML needs to understand how the action the intervention will be perceived by the system, and how the system will react to that intervention. And then the other part is explainability, right? So you want to be able to understand complex models and understand what the kind of changes that they are making to your system, and also how you are accounting for causal effects, right? If you go and intervene on your network system, how is that gonna, how the system is going to behave to that? So I think that one of the main visions of that we have is that we want a robust, causal, and verifiable machine learning for network systems. And so what we are doing is combining cutting-edge ML techniques with domain-inspired insights to get more robust solutions. And so one of the key points is that just using the existing ML tools doesn't seem to be enough for networking. So today we're going to talk about two parts. Two works that we have that fill in this kind of vision. One is on traffic engineering with ML, and the other one is on causal queries for video streaming traces. So we start with this notion of wide area network traffic engineering. So we have these input matrices, which are demands in the future. The first part is that you have to predict what the demands look like in the future. The challenge is that that is really hard to predict how the future demand will be, because there are a lot of very difficult to capture correlations in the data, so that when you have some kind of a event, the burst of traffic or some burst of demand, it's hard to capture that because it might happen correlated in many different source destination pairs. And then you feed this prediction to some optimizer, which then decides, and the capacity antennas to decide how to route the traffic on the network. There is another interesting aspect of this, is that it will not always the solution that the optimizer gives you. Sometimes you cannot really implement that exact solution. You have to change because your equipment has some quirks, some requirements that is not really met by the optimization that you have. So you have to go adapt with heuristics. So what happens today, if you think about kind of abstractly, is that we have a real problem, which is very complex, right? And then what we generally do, we look at this complex problem and spend a lot of time thinking how to make it simpler, right? So that we can use the tools we know, say linear programming, right? Integer programming or other tools to then approximate this problem as well as we can. But the reality is, I think that it's generally, if you think about an elephant, it's like trying to approximate an elephant but with a ball in vacuum, right? Like that's generally what the simplification looks like. And then we go and use an algorithm to solve that approximation. And then reality is that once you get the solution, that solution doesn't fit reality because you have to approximate in many ways. Then you have to adapt it, right? So for instance, for traffic engineering, the switch may have table constraints, and then you cannot implement that exact solution. You have to change it. So then what I would call the problem, right? Like you do all this work, and in the end, your solution doesn't quite fit, and you have to spend a lot of time trying to adapt it and make heuristics for it. So what is the kind of promise of machine learning would be to try to go from the real problem more directly to the solution, so that the complexity is handled by AI. rather than us trying to simplify the model. And in this promise, right? What is interesting about it is that for instance, I can just give, instead of giving the future demands of the traffic matrices, I can just give the current ones. I can give the current capacity on tunnels, and then I can ask the neural model to predict what the best traffic split will be for the future capacities, the future tunnels, and the future input matrices, so that it's really able to learn to adapt, rather than me trying to predict what the future looks like. The machine learning model will try to, by itself, make a traffic split that is robust to all these changes that could happen. And that's kind of the interesting direction for traffic engineering that has been explored in some of really interesting papers recently. The one problem with challenge with this type of application is that if we just get off-the-shelf machine learning, it doesn't work too well in this scenario, because the network may have failures, right, in the future that you're not seeing yet. There may be demand spikes, right? There are many unexpected things, and in real networks are like this. They can change quite a bit, especially data center networking. They change quite rapidly. So off-the-shelf models will be vulnerable to these new scenarios, right, that you haven't seen in training data. And then you have what the challenge is to make your neural network robust to this type of what we call auto-distribution settings. So first thing, let me explain, for instance, one case why we have to do things differently in our work on HARP, which was published at SIGCOMM 2024. So the first principle we wanted to have is that if the tunnels have changed, right, between training and test, but essentially just being reordered, then the neural network should not care about it. It should be able to produce the same solution, right? And also, if you change the direction of some of the links, like the flows, if you do a transpose of the traffic matrices and the links are symmetric. So there are many ways in which you could essentially change the input, but the output of the neural network should be the same, or should follow the same type of pattern of the input. And this in machine learning we call equivariances or invariances to input transformations, meaning that the neural network is not susceptible to these changes of the input. So here, for instance, we show an example where the tunnel IDs have changed because we have to recompute the tunnels. And the fact that the IDs have changed doesn't mean that you should change the split, right? It's just the IDs are arbitrary. So off-the-shelf models generally will not ensure this objectives remain the same. So that's one principle, right? That we have to be kind of able to when irrelevant changes in the input happen, our output remains the same. The other important principle is to align the neural network architecture with the optimization model. And the reason for this is because if you have a new completely different, like if your topology somehow changed very abruptly. So you see in training some topologies, and then your neural network is very accustomed to that. And now in test, you look at the topology has changed quite a bit, right? When you deploy it because of some failure event. Then you want your neural network to be able to be robust to those changes that you never see in training. And therefore, one of the principles of HARP is to what we call neuroalgorithmic alignment. So it tries to mimic the way that the optimization method works. So that because an optimization method doesn't care about the topology, right? It always works in any topology. So if the neural network more closely mimics how the optimization works, then it is more robust to these changes. Okay, so these are the two basic principles. And then, so what we are given for HARP, for instance, you have the topology and capacities. We model the tunnels, and we model the initial routing predictor. And then we also have a system that will, just a bit like the optimization, linear programming optimization, it will look at the solution and decide if it's not good and try to adapt it. But it's a lot faster than optimization methods. So what's the design like? Well, we are given topology and capacities. We go into a graph neural network because that's what the topology is, right? It's a graph, and has a graph neural networks has the right types of equivariances for dealing with changes in topology. Then to model the tunnels, we use a set transformer. And the notion here is that what is a tunnel, right? What is it's essentially a sequence of links in the network from which the traffic from A to B is going to go. But if you look at the actual, what matters on this link for our task, right, of routing traffic, we really don't care the order of the links in this path, because the maximum capacity between A and B is defined by the bottleneck. So therefore, when we represent this path, we just need to represent as a set of edges, because the order of the edges is irrelevant for defining what the bottleneck is. And that's very important for us, because that will make our method a lot more robust to changes in topology. So then we are given a traffic set of tunnels described as a set of edges. And then we model these tunnels through this invariance to reordering of the edges, essentially. Then that creates tunnel embeddings. And from the tunnel embeddings, we are going to be given the input traffic matrices, generate the initial routing. And after that is where the neuroalgorithmic alignment or reasoning comes, right? So you are given a initial routing now that may be not yet a good routing for this network. So what we'll do is similar to how the LP optimization works. We are going to score this solution and then apply a recurrent adjustment unit, which we adjust this initial routing to reduce the violation, the constraint violations in your problem. And then we do this a few times, and finally we get the final routing. So this alignment is actually, with the RAU, is incredibly important because it allows it to be a lot more robust to changes in topology and changes in traffic demands. So that just quickly go through this part. The way that our system works is that we're really like looking at predicting the future. So we have we cluster the network topology and traffic in a few clusters, and then give the model these clusters and try to predict the next cluster. So how does this compare against, say, optimal, like the actual trying to solve the LP problem, right? The optimal traffic demands. Well, the thing is that when you're trying to solve the actual routing with the linear programming, you are essentially trying to predict the future, right? You're trying to predict your future network topology. You're trying to predict your future traffic matrix. And therefore, when you predict something, then your solution is as good as your predictions are. And the thing is that it's a lot harder to predict what the future traffic demands are going to be than it is to build a neural network that is robust to many different changes. And therefore, if you try to predict and then apply optimization, which is in black here, you can see that it's a lot worse than the neural network, which it has optimized seeing examples of these changes, specifically because the traffic bursts can happen in a very non-trivial correlated way across the network. So it's really hard to predict how these correlations happen. So the other thing is that, is this important to talk about these invariances, right? The changes in tunnel ordering, changes in the topology that can happen between train and test. So if you compare against, say, more off-the-shelf methods, right, that use more off-the-shelf neural networks rather than one designed specifically for networking, you can see that when you shuffle the tunnels, like when you change the tunnel IDs, the kind of off-the-shelf methods, they have a worse performance because they lose performance because they are not invariant to these changes. So just recomputing the paths is something that affects off-the-shelf ML. So, and then I'm gonna switch to Sanjay. We'll continue from here. Sanjay?
Yeah. Can you see my slides?
Yeah.
By the way, maybe we can take one or two quick questions, and then I can continue on this, and we can have more extended discussion after. The questions from the audience, or
Yeah, that sounds good. Let's see. Edmundo, do you want to ask the first question? Let's see. I think you might be on mute, Edmundo. Let's see.
Sorry, no, Matt, go ahead with the audience question, please.
Oh, sure. Let's see. There is an audience question. It's about, I don't know if you guys have thoughts on this in particular. The first audience question is about quantum machine learning. Do you guys have any thoughts on that? Applications of quantum machine learning in communication networks? Is there a need for kind of quantum speed up in telecom networks problems? Any thoughts on that sort of thing?
Actually, I haven't given a whole lot of thought to that area, but I know, Bruno, if you have any ideas.
Not really. I would say that one of the challenges in machine learning has been energy. The current GPUs consume a lot of power, and they are pretty slow at communication. So if you notice a trend, what the trend is that we are reaching a wall with silicon. So we made one computer into multiple networked computers, and then they're becoming bigger and bigger to the point that the next wave of GPU data centers will be distributed globally, because there is not enough power in one location to feed these GPUs, right? So you have to distribute them geographically even. That is a big problem, right? I think we are going to eventually have to change to some more efficient forms of computing, and quantum computing definitely is one of them.
Should we ask one more question for you before you proceed? Do we have a question?
There is a comparison on HARP versus others. I think that's a question.
Yeah, I could possibly take that. So we do have a lot of detailed comparisons in the SIGCOMM paper. I think one thing I would emphasize is, some of those other papers are definitely work that has inspired us very much. So we are definitely building on top of some of that work. And a lot of the benefits that come in is when you have dynamic environments, right? So I think I see those initial works as inspiring us towards using ML for TE, but the solutions typically focused on a static topology which does not change over time. The interesting, a lot of our evaluations show that when your topologies change continually, right, or you train on data where the topologies change, and then at test time your topologies might be different. our models are able to work in those sorts of scenarios, and they give substantial benefits as well. For example, if you train on a topology without failures and you test on a topology with failures, you get pretty significant improvements because of some of the mechanisms in HARP. Okay.
If I want to add to Sanjay's thing, there were, at the time we were doing this, there were no off-the-shelf ML architectures for this. We had to build one from scratch. So I think networking is a very rich area to build new ML methods.
Yeah.
Should we? Okay, go ahead, Sanjay.
Oh, I was just wondering if maybe I could continue with the second piece, and then we
Sure.
can come back and have more discussions. Yeah.
Sure.
So with that, I want to talk about our second piece of work that Bruno and I have done together, and this is joint work with our PhD students, Chandan and Jianfei. So this is a very common task in networking, right? So we deploy a system in the wild, we collect traces from it, and then we want to ask some questions on what would happen if I make some changes to it, right? Just very concretely in the context of video streaming, you might say, what would happen if I use a different adaptive bitrate algorithm, or if I add a new quality, or I were to reduce the buffer size and so on. Now, what really happens today? If we talk to many of the practitioners, a very common practice is to use trace-driven simulations where you collect data from users from past sessions. And in fact, this is also something that we use a lot in the research community in some of our evaluations. Unfortunately, these techniques can suffer from biases due to hidden confounders, and I can give you some intuition on where these confounders come in from. The other kind of strategy is to use randomized controlled trials, where you might do some kind of A/B testing and kind of test the system on a small number of users first. But one of the challenges with this is that it affects the performance of live users. And so it's something that you would typically do with a lot of discretion in practice. So there's typically a lot of behind the scenes analysis that goes on before you're willing to actually try out something using an RCT, right? So our work here really focuses on this question on, can we tackle these what-if questions without explicitly doing an RCT? And our work is sort of focused on video streaming, though we believe some of the principles can apply to other settings as well. And we've developed a framework that tackles this notion of causal reasoning and reasoning about changes to the system. This is actually an area that is widely used in other domains like epidemiology and so on, right? It turns out to be a fairly complex problem in general, but we have also been able to show how, by leveraging some very unique insights in the context, in the domain, you can really simplify this task. And so I'm going to give you I guess most of the audience is familiar with adaptive bit streaming. You have a video server in a client, you're transferring data over a variable bitrate network. You might encode video at many different qualities. And each client can request a chunk, which might be 2 seconds of video, for instance, at a different bitrate, and it has the ability to switch bitrates across chunks, right? Now, the first thing that we would notice is that the adaptive nature of the system makes this bandwidth a hidden confounder. So what this graph is showing you is on the x-axis are chunk sizes, and the y-axis is the download time for those different chunk sizes, right? So what you can see is if the chunk sizes are small, or at least what a reasonable expectation would have been is to have a monotonic trend where larger chunk sizes lead to longer download times. But what we actually see is something quite different, where when it seems like we are seeing an increasing trend and then it's coming down again and becoming an increasing trend. Now, why is this? Well, this really stems from the adaptive nature of video streaming, because when the network bandwidth conditions are very good, your video quality chosen is high, But when the conditions are poor, then the quality chosen is also low, right? And so you might end up finding that although the download times are very similar, although the underlying bandwidth is quite different. Another kind of confounder is a TCP state, right? So the actual throughput that you get may not be may not reflect the true intrinsic capacity that the network is capable of. So it might depend on things like the size of data that you're transferring, what kind of TCP state you have at the start of the download, and so on. So and that's sort of illustrated in the graph. The other kind of issue to keep in mind is that you could have these cascaded effects. For example, imagine that your intrinsic network bandwidth is a time series as shown, and then you have deployed the system and downloaded a series of chunks. Now, suppose you made a change to the system, it would result in a new time series, a new set of when each chunk is downloaded and when it finishes, right? And something that's interesting is even the change to a single chunk can really impact the start times of future chunks and so have this cascaded effect throughout the session. Okay. So how do we really reason about all this? So what we did is built a model of video streaming, and this sort of gives you some intuition. So imagine that you have a client which starts with a buffer. It downloads a chunk with the size SN, right? It observes a download time. At the end of the download, the buffer becomes, there's a change in the buffer state. It becomes a buffer EN, and you observe a throughput in the process of the download. Now, this is a time series. So that what is shown on the left is for chunk n, but then you also have to go back in time for chunk n minus 1, n minus 2, and so on. And you have here an intrinsic network bandwidth, which is also a time series. And notice that we show this in white to represent that these are hidden variables. So these are not readily observed, whereas the ones that are shaded are things that we can easily measure. So if you go deeper and model all the dependencies, you'd get a very complicated graph like this, right? We don't need to go into the nitty-gritty of the graph, but this is just sort of capturing what depends on what. For example, based on what the intrinsic capacity is and the initial buffer state, that could influence the size of the chunk that you pick, and that can affect the final buffer state, and it can impact the download time and so on. So really the causal inference problem here would be about saying what is the intrinsic network bandwidth, right? So what can you, how can you really use the observed data to infer the intrinsic bandwidth? It turns out that if you use some of the very standard tools that are available.
Sorry, just to make one note.
Yeah, please.
So if you don't mod, if you ignore this white boxes, then your decisions at any point in time will depend on everything that has happened from the past, every single gray box. And then every decision you make will affect all things in the future. So it really is incredibly difficult to model this. And I'll say also that in this case, reinforcement learning is not going to help you because of this confounder. So these white boxes are confounded, and reinforcement learning will not, because these confounders, if you have some change in the test distribution of them, it's going to get confused. So just added this one.
Thank you, Bruno. Thanks for that. So if you're convinced that this is a fairly nasty problem, and this is where I think you can come in with practical solutions from the networking context, right? And one of the observations that we made is that if you could observe the TCP state at the start of each chunk, which is something that we could do. It's not routinely done, but it's something that you could do. And by this state, I mean things like the congestion window parameter and things like that. Then notice that it kind of flips the state of this variable from a white to shaded, which makes it observed. And while we won't have time to get into the specifics here or the details, this really reduces the complexity of the causal reasoning problem, right? There are certain, for example, there's this notion called deseparation, which means that you can make certain independence assumptions that are not possible in the absence of observing that state. And what that really means is that you can now bring a variety of other tools to bear. So for example, we designed hidden Markov model, a more customized version of it, and adapted that for the inference issue. So I think the crucial insight here is that if you were to really solve the causal inference problem in its most general form, it can be pretty nasty because of these time series dependencies and the fact that your decisions now could depend on the past and so on. But some crucial domain insights can really sort of simplify the problem and allow you to make inferences in a more amenable or tractable form, right? So here's just some very quick evaluation just to give you the kinds of things that we can do with this method. So you imagine that we have deployed a system on the left in setting A, and then we kind of, to evaluate, we sort of emulate certain traces. We know ground truth for that reason. And then we would use this Veritas tool to kind of create samples of those observed logs and then play back those traces that Veritas infers on setting B and get a variety of answers. Now, one thing to note is that in Veritas, we don't assume that there is going to be a single right answer. So it kind of intrinsically captures some of the uncertainty in this inference process. So it could give you multiple different inferences that kind of capture what it thinks is the hidden variables. So here's an example to illustrate the kinds of results we can get. Imagine that you've deployed the system and it uses a set of qualities. It uses low quality video, but you want to ask the question, what would happen if the system had changed to a high quality video? How would it have performed on those traces, right? Now, what I'm showing here is the performance if you could emulate ground truth. SSIM is a video quality metric and the rebuffering ratio. So this is what would have happened in practice if you knew ground truth, if you had switched from low quality to high quality. So now what we want is for any trace-driven approach, any data-driven approach to be able to be very close to the ground truth, right? So that would make it a good method for predicting the answers to what-if questions. So what we see here is the red curve is a baseline, which is simple trace-driven simulations where we take those bandwidth traces as they are from the deployed system and use them for prediction. Now you can see that the red curve is quite off from the ground truth, right? So it kind of underestimates the SSIM and overpredicts the rebuffering ratio. On the other hand, if you could use Veritas, you get predictions which are much closer to the ground truth. So it's predicting video quality and the rebuffering much better. So that's basically what we wanted to share. But I think in conclusion, we've given you what I think are just two initial examples of what can be a very exciting direction, a research agenda for the community. So HART, which is a neural scheme that's transferable across topologies. So we want to get across the idea that it is possible to design schemes that can start working on scenarios that are not in distribution. And then we have presented Veritas, which is a causal framework for what-if questions related to video. So we have artifacts in this available for those interested. But really, we have a much broader message, which is I think there's a very exciting opportunity for cross-disciplinary approaches to ML-driven networking. Clearly, ML is interesting for us as networking folks, but it's also exciting for ML researchers because of some of the complexity of network problems. And with that, we'll be happy to take more questions and have more discussion.
Okay, thank you very much, Sanjay. very interesting. And we have questions for the audience, but before that, I guess Matt and I would like to ask two questions. You mentioned challenge reliance on historical data. It's not fully capture the future, the real world conditions. And what are your thoughts and advice to students? So it's particular to students while researching those modules, and so that they can generalize well to unseen scenarios. And what are the key pitfalls that students should be aware when trying to training, model training, and in fact they are investigating this other approach, ML approach.
Bruno, you want to start? Or
Yeah, I can give a advice.
Yeah.
So get any paper published in ML for networking, and train in under some conditions of the data. Now change the conditions and see how they react. Probably if it's off-the-shelf ML, it's not going to react too well. And then start coming up understanding, like, why is it that is not robust, right? And you will see that this off-the-shelf ML cannot be applied there. You have to specialize to that specific task. Just try, download the code, train on some condition, change the condition in test, and you'll see it. You will see what happens. I think there's a lot of work that are needed still to fix these issues. And also in ML, like in ML, there are many settings that we don't know how to solve. And I think networking can help ML a lot on this, because you folks have a lot of data, have a lot of interesting cases, and to build more robust ML, maybe networking would be a key aspect for the future.
And one thing I would add here is, there are a lot of ML techniques, but collecting data is quite valuable, right? And that's something that is a strength for our networking community. So I've often found that it's very useful to just spend time thinking how you can collect the data, what you can get, and and that already kind of teaches you about a variety of very interesting sorts of things. For example, there was a collaboration. We've been looking at things like predicting throughput for video streaming. And we did some very interesting measurements, which told us that usually you could think of throughput as dominated, or video download times as dominated by throughput. We got data which showed that it might depend on latency as well, because of the initial time to the first byte, right? We also found cases where in a CDN, your chunks could be downloaded from different layers in a CDN hierarchy, and all this kind of influences some of the ML that you do, right? So I think given some of the rich heritage of getting insights from real data, I think I would definitely encourage students to continue building on that heritage. And I think there are, ML is a nice add-on, but you can't do any of the ML without the data to begin, right? So.
I'll add one thing to this that Sanjay is saying, which is very important, what he said, is that before collecting data, my suggestion is build the causal DAG that related to your application, because we did not know that TCP state was so important, and we were not collecting that.
Thanks a lot. Matt?
Yeah, that's great. So we had another question too. So your work is amazing because it's this very deep synthesis of two very different areas, machine learning and networking. And we were wondering if you had any advice for graduate students or researchers who wanted to kind of make a similar sort of jump and connect across areas.
Yeah, I could maybe start with this. So I would expect that this is going to be a longer journey, right? So Bruno and I have started this collaboration back in 2017, and it has gradually evolved over time. I think, it might be good for students to take classes in both topics, both networking and ML. And when you take classes in ML, it should not just be courses that teach you how to use ML, but go a little bit into the theory, right? Even if you're not going to do research involving the theory, I think it's very useful to understand some of the language and understand some of the insights behind those tools, right? Another thing that's worked very well in our collaborations is usually we have a student with an ML background and a student with networking background, and I think those interactions have proven very beneficial to both students. Bruno, I don't know if you want to add.
No, that's it. I think the students, you cannot be afraid to talk to a ML student and go tell them, I have this problem, I tried this thing and it fails miserably. There is this, and then the ML student will probably be quite interested in why does off-the-shelf ML, all the techniques they know don't quite work. You have to be adapted to your scenario.
Thank you very much. So we have two questions from the audience. Matt, do you want me to read or? Yes, I'm.
Yeah, sure.
I read the first one.
Yeah.
Okay,
Yeah.
I read the first. What does it means? What does it mean exactly to shuffle the tunnel IDs? Are the IDs meaningful or are they just numerical codes?
Yeah, they are not meaningful, right? So when you recompute the shortest paths and the alternative paths, the algorithm will output will make decisions. If your network has changed a little bit, it may change, like some of the existing paths that was path number 10, now it's path number 12. And that doesn't mean anything, right? The numbers are irrelevant. But the thing is that a lot of the off-the-shelf ML will treat them as different just because they change their ordering. So you have to be careful. You have to build neural networks that are not sensitive to these irrelevant changes.
If I could just add, I think there was a question on why there's a second part of it, why the method is more robust. I think one of it is because you're representing it as a set of edges, right? You're not representing it as a sequence of edges. I don't know, Bruno, if you want to chime in more on that.
Yeah, so if you can imagine like an equivalent configuration of the network where instead of going one way, it goes the other way, but these two edges here really like are not the bottleneck. The bottleneck edge remains the same. The path has changed, but the bottleneck edge remains the same. If you treat it as a set, you know that. But if you treat it as a sequence of edges, that the representation, the embedding that you create for this edge will change. While if you represent as a set, it won't. It's still the bottleneck edge. The rest of the edges don't matter, right? So therefore, the network, your neural network understands what it's more aligned, right? Understands what it's trying to optimize. It really cares about the bottleneck. The rest of the edges are not that important. So if you represent that way, the performance gains are amazing, and the robustness increases a lot, right? Because even if the path has changed a lot from the beginning to that edge, to the bottleneck edge, and through the bottleneck edge forward, it doesn't really matter, right? Because the bottleneck remains the same.
Makes a lot of sense. Matt would like to read the. I think we should move to the other to give a chance for everyone to ask. Could you read about the?
Yeah, sure. So there's another question about machine learning seems very important for network systems. What important problems or research topics should graduate students focus on when they, kind of are looking for problems? Do you have any ideas about what kind of areas might be interesting for them to look into? Any thoughts along those lines?
I have a feeling that there's going to be machine learning in a lot of different contexts, right? So you could start thinking of CDN provisioning or allocation problems in data centers, GPUs, and so on. But I would just make one caveat, which is, at root, I still remain a networking person, and I would encourage people to view ML as a tool that can solve a real problem that one cares about, rather than start with I have ML and what can I do with it, right? So, you'll often find that there are many problems in many practical settings where ML is just natural, um, right? But I wouldn't go searching for a problem where you can apply the ML. That's just a meta advice that I would give.
I think my advice would be talk to the actual network operators, and when you see something that they are doing that involves a lot of like simplifications and abstractions, and then when they get the solution, they have to do a lot of heuristics to implement it. Maybe that's prime for an ML procedure.
Great. There is a question from the audience. Are digital twins for networks feasible? And can network digital twins coupled with these ML-based optimization methods be something that can be used to closer replicate and optimize real networks?
Yeah, that's actually a very interesting question. More broadly, we are doing some work. We're interested in this area of sometimes you cannot model the network very nicely by simple optimization models or simple tractable mathematical models, right? What if your system really has to be captured with a simulator of some kind, and then you use an ML model to kind of optimize decisions where you'll only get the final result based on the simulator, for instance, right? So that's a area that we are quite excited about and something that we're looking at.
Bruno, you want to add?
No, I think Sanjay said everything.
Matt, I guess there is one more question for the audience. Then we move to some other question.
Oh, yeah. So there's a question about programmability in networks. There's a push towards softwareization with software-defined networking, P4, programmable data planes, SmartNICs, DPUs, etc. Will future network engineers be software engineers? Do you have any thoughts on how kind of this machine learning stuff is affected by programmability in networks? Are there any kind of relationships there? Any thoughts on that?
Yeah, so I guess that's slightly tangential to our talk, but I think I also do work on the SDN programmable switch space, and definitely I do think raising the level of abstraction is the way to go in just about everything in networking. So we should be thinking the network as a whole, not individual devices, right? We should be thinking higher level intent, not what configuration runs on each switch. And I believe ML can actually play a role here, right? Because, going back to the slide that Bruno presented, oftentimes we develop heuristic solutions on simplified models, but ML gives us the opportunity to develop techniques on the direct higher level problem itself, right? And I don't know, Bruno, if you want to add more. But,
No, that's
by the way, Matt, there was a question on the chat which I thought was interesting.
Go ahead, please.
There's a question on the papers with code. I think the question was about making reproduction of research easy and iteration fast. So, what are your opinions on applying this open source effort in ML for networking into a formalized environment? So, I'm not completely familiar with that site.
Yeah, I can talk about it.
Yeah.
So 100%. Actually, in our panel on SIGCOMM, I recommended that I feel the ML community, the networking community, could have a set of benchmarks, right? You want to do traffic engineering. Here's a data set. Here is a distribution shift, right? A topology shift that your method should achieve. And then you have some kind of benchmark and you publish and you have a ranking. That has done wonders for machine learning, like having clear benchmarks, very difficult tasks that everybody works on and share their code. I think that would be fantastic.
And if I may ask a continuation of that question, what do you recommend, say, for us to collect from the network, say, given that we have efforts in the wild that collects measurements or real measurements? What do you recommend? What do you like to see that we collect mostly to have these data sets?
I think that would be very problem specific, right? But for example, in traffic engineering, we're looking at certain things like traffic between pairs of sites and so on. In something like video streaming, you're looking at things like download times of chunks, inter-arrival times of different download requests, and so on. So that definitely be problem specific.
But I was meaning more like MLab kind of data collection effort that you collect a lot of data from.
Right. But one thing I did want to say, Edmundo, if you don't mind,
Sure.
if it's taking a slightly different direction, but one of the challenges I would say to this open data set is a lot of the research that we do in the community, we get data sets from industry, and some of these are proprietary, right? And I would say one challenge that we have is that you may develop paper one may develop technique one, which is tested on private data set one. But then when paper two tries to do it, you're not able to replicate the results on a public data set or create those sorts of things. And then there tends to be some challenges in how you fairly represent the prior work, right? Because so it's not because you can't quite share your new data set where you're getting these results which are not so good, but at the same time, the authors of the previous data set haven't had a chance to try it here. So there are going to be these tensions on how we resolve it, and that may be something for us to think about as a community. These open data sets would definitely be helpful, but there is also going to be the reality that we're going to be doing a lot of evaluations, private data sets as well, right? So
one thing I would say on this that's important that Sanjay is bringing up is I believe that we don't need data. What we need are scenarios, right? Like specific scenarios where that happens in say industry in a private data set that are replicated. The data is very different, the topology is very different, but that kind of scenario is similar, so that your method, if it works on the public scenario, it should work okay in the private one. If you have scenarios, it would be quite interesting to move towards rather than sharing data, sharing more scenarios.
Thank you very much, Matt. I think we are away. There are several questions in the audience, but it's we're 2 minutes past the hour. So.
Yeah, thank you, everybody. We want to thank the panelists very much for their insights and putting together such an interesting event. We're going to have a recording of the session put up on YouTube. It's going to be linked off our main website. And if you have questions that we didn't get to, or if you want to continue the conversation, we have a Slack workspace. The information is in the chat. Please feel free to join that. And in 2 weeks, we're going to have our next event. So feel free to join us for that as well. So thank you very much.
Thank you very much.
And thanks to Matt and Edmundo for organizing this and for everyone attending. We'd be glad to take more questions offline if you have me. So
yeah. That's definitely Edmundo, Matt. Thank you so much for inviting us.
Thank you,
Bye.
everyone. Bye.